Hey guys, so let's discuss new round from Microsoft, which is round 2, coding round 1. And here we will be seeing the problem design and implement LRU cache. So I have already created one video on LRU cache in data structure playlist, but here we will be discussing more in depth. Okay, we'll see the follow-up questions and we'll see the answer based on 3 roles, which is software engineer, senior software engineer and architect. Okay, so before starting the solution, discussing solution on this problem, see, this is the one of the most common Microsoft coding interview question. Okay, you will see this kind of questions, this question many times. Okay, unlike Amazon, Microsoft interviewers usually expect you to write working code, okay, explain time and space complexity, handle edge cases, and then discuss design trade-offs, extend the solution for the production systems. Okay, now let's say um, expectation differ by levels. Okay, so if you talk about software engineer, 2 to 5 years of experience, correct implementation with order 1 operations is needed. Okay, senior software engineer, 6 to 12 years of experience, they should able to tell more about thread safety, TTL, okay, time to leave, eviction policy, and testing scalability and memory optimization. And then for principal software engineer, 12 plus years of experience, so he would be able to discuss about distributed caching, persistence, monitoring and architect trade-off. Okay, architecture trade-off. Now software engineer, what he will be answering for this, right? So expected answer would be, he will be saying that LRU means least recently used cache, evicts the item that has been accessed for the longest time. Okay, that has not been accessed for the longest time. So here get and put operation will we will execute in order 1 complexity or the constant time, and evict list recently used item when capacity is exited. Okay, so now high level design, if you see here, we will be using 2 things. First one is HashMap, second one is doubly linked list. Okay, so HashMap structure will be something like this. You will have a multiple nodes, okay, with key value pair, and then in doubly linked list you will be having this node, previous and next pointers. Okay, and then head and tail, 2 nodes of that doubly linked list, and this is bidirectional list. So where you most recently used item you will be adding after head. Okay, and least recently used items you will get from the tail. Okay, the previous element, so this is the tail and previous element of tail is the least recently used element. So now why we are using this design, see here we are using HashMap and doubly linked list. Okay, so HashMap provides order 1 lookup when you want get key, so it will get the item in order 1 constant time, and doubly linked list maintains usage order, right? So moving a node is in order 1 complexity and deleting the LRU node in order 1. That's why we are using here doubly linked list. Now Java implementation, if you see, so you will be, see, the concept is very simple. You will have one hash map. Okay, you will have one hash map, let's say HM. Okay, and then you will have one doubly linked list. Okay, so this is head, this is tail, let's say, and this is node, this is previous, it is doubly linked list, this is next. Okay, similarly previous, next, previous, next. So now when I ask you to get, let's say in this we have a element 1 2 3. Okay, 1 2 and 3, and this is head, and here somewhere tail. Okay, so 1 2 3 is there in the doubly linked list, and similar 1 2 3 will be there in HashMap also. Okay, 1 comma 1 2 comma 2 and 3 comma 3, let's say key value pair. Now if I say get 1, okay, so get 1, it means that I am touching node 1, right? Now it is not least recently used. So what I will do, whenever I apply any operation like get or put on that particular node, I will delete that node from HashMap. Okay, so get 1, I will delete it from HashMap, and then not from HashMap, sorry, get you don't need to delete, right? So in get will be there only in HashMap. Okay, get 1, but you will check whether it is there in HashMap or not. If it is there, then you will proceed further. Otherwise, if it's not there in HashMap, it means you don't have that node. Okay, so let's say you apply the get, you are performing get operation, so you will check in HashMap, yeah, it's there. So you will get that element from linked list. Okay, and you will delete that element from linked list. Now where you will add that, after head. So currently, yeah, it's after head only, so you will again create one node, and after head you will add that. okay, 1. Now next time 3 will come, okay, get 3 operation will perform. So you will check that 3 is there in HashMap. Yes, if it is there, then you will delete it from Doubly linked list. Okay, so I have deleted that from Doubly linked list, and I will display its value, which is 3, and then again I will add after head. So now 3 will come here. So now my linked list will be like this: head, then 3, then 1, and then 2. Whenever someone will ask me to put let's say put 5, and the capacity is already 3 for this, okay, so we are already on the capacity is full for us, right? We need to delete one node, let's say before inserting 5, okay. So you need to perform put 5, but you don't have a space, so you need to delete one element. Which element you will delete? The least recently one, right? Least recent used. So 3 you just used, 1 you just used. So whatever you have near this tel, okay, previous element of this tel, you will delete that element, okay, blindly. So I will delete this 2 from here, and then I will add this 5. I will delete from HashMap also, okay. I will add then 5,5 in HashMap, and then again 5 I will add here after head. So now my linked list will be head, 5, then 2, and then 1, sorry, 3, and then 1, and then 10, something like this. So this is how this one will work, okay. Very simple. Just only these operations we need to perform. So let's see the Java code for this, equivalent Java code, okay. Okay, what is happening here in Java code? You have one class LRU Cache, okay, and inside that class you have an inner class node. So node structure is key, value, previous, and next, something like this. Now you will have one capacity inside this LRU cache class, okay, capacity of the doubly linked list, capacity of a cache. And then I told you that you will have two things, okay. First one is HashMap of type integer and node, right? So and then so you will have the HashMap of type integer and node, and you will have head and tel as well, okay, two nodes. And then this is the constructor of LRU cache. What you are doing, you are just first time you are just telling that let's say capacity is 3, you need to create a cache of size 3. So you will pass this capacity here, okay. What it will do, it will create one map, okay, and head and tel will be pointing to 0 0. Initially head ka next point to tel, okay, this is head, this is tel, so nothing is there. That's why head ka next pointing to tel and tel ka previous is pointing to head. So this is what it will do, okay. So 0 0 0 0. Now when you we will see here two operations, get and then put, right? So if you wanted to get element from this cache, what you will do, first you will check whether that element is in map or not. If it is not there in map, then it means you don't have that element, return -1. If it is there in map, just get the value of that node, okay, remove it from map, and then again insert it into the remove it from linked list, and then insert again in a linked list, but after head. So this is what these two functions are doing, and then you just return the node key value, right? What is happening in put? So you need to put some key and value in a let's say double link in a cache, okay. If the capacity is 0, you can't put any value, the capacity itself is 0, okay, you cannot add the element, so just return directly. Otherwise check if it is in map. If it is there in map, then you get that node, okay, value, and then you will remove it from linked list. Again you will insert it into the list, right, and return. Now if your map ka size is equal to capacity, in that case you have to delete element from tel, right? So tel, just take that element node tel ka previous, right? So that is the node. You just remove that node, and then you remove it from map itself also, okay. And then after that you just create a node, and then insert that node after the head, right? And then put again that in a map. So what remove function is doing, remove, you need to remove from tel, right? So whatever node you have to remove, let's say, so node ka previous ka next, so remove means you need to remove I have given the node, okay. So it's a this is, let's say this is the node, okay, and this is its a previous, and this is its next, and you have some other node here and some other node here, okay. So what you need to do, if you need to delete this element, okay, what you need to do, so this is node, so node ka, and this is the node ka previous, and this is node ka next, okay. So nodes previous next will become this node ka next, right? This is what is written. And then similarly you will do this, node ka next ka previous is equivalent to node ka previous. That's it. You just need to adjust the pointer. And insert, what you will do, so you will insert that element after head. So let's say this is your head and you need to insert here. Okay, so what you will do, head ka next equal to node ka next, head ka node ka next is, so this is your previous and this is your next. Okay, and this is your node, let's say. So node next means this one. So initially head ka next was pointing to some other node. Okay, now you need to insert this node here. So what it will, so node ka next will become head ka next. Okay, and then node ka previous become head, and similarly head ka next will become node. Okay, head ke next ka previous become node, means this node's previous we are adjusting, and then next also head ka next equal to node. So that is how we will adjust the pointer. And the complexity will be for get put operation, it will be order 1, and space complexity will be order of capacity, because we are creating the doubly linked list, right? So that's why. Now senior software engineer, he will answer these this implementation. Okay, apart from that he will also answer that basic implementations of the interview problem, but in production I would consider concurrency, expiration, memory efficiency, observability, and testing. Okay, so concurrency, if multiple threads are trying to access the same node value, then what will happen? Okay, so both will delete the element, then what will happen in that case? Okay, and then expiration also, for how much time you need to keep that node in a memory. Okay, TTL, because we are implementing here cache, so, and all those things. Now the production architecture will be like this. So client requests data through some API, let's say, and that data will we will get it from LRU cache. Okay, so fast in memory cache layer for frequent access data. So LRU cache, what will happen inside LRU cache? You will have one HashMap. Okay, you will have one doubly linked list, and then you should have TTL manager, time to leave manager. Then for observability you should have a matrix. Okay, where you will track your hit ratio, miss ratio, eviction latency, and then size, etc. And then after that you should have a locking for concurrency control, right? So ensure thread safety for concurrent access. Now enhancements, what enhancement he will be doing here? So thread safety, TTL support, matrix monitoring, beta testing, and memory optimization. So this thing he will be doing. Now the simplest way to make the thread safe is to protect the HashMap plus doubly linked list. See, here we are using two things, HashMap and doubly linked list, and if you protect these two things, then your system is concurrent. Okay, because get and put operation we are performing on these two data structure only, right, as a single shared data structure. Okay, so HashMap and doubly linked list, you make it as a single shared data structure. Okay, since get is also modify the list, like if you want to get something, so you are deleting that element from linked list, right, and then you are putting it after head. So get is also modifying here, it is not only read operation. So both get and put must be synchronized. Now thread safe version, if you see of this program, okay, using ReentrantLock, we will see what is ReentrantLock, ReadWriteLock. Okay, so you don't need to do anything, the program will be as is. Okay, it's just the get and put function we need to protect. Okay, so whenever you are calling get, okay, you will just call this log.lock method, and then it's a finally block, you unlock that particular method. Okay, similarly for put also, log.lock method you will call, and then in it's a finally block, you just unlock it, right? And but there is one problem here, and we will discuss that problem also. So now principal engineer or architect, what he will answer, the expected answer would be an in-memory LRU cache works well for a single GVM, right? So at enterprise scale, I would evaluate whether a distributed cache is needed and separate local caching from shared caching. Okay, so enterprise architecture will look something like this, that your application will be here, and then you will be having local LRU caches. Let's say you have 5 instances, okay, 5 servers, so all 5 servers will have their own local LRU cache. Okay, and then you will have one distributed cache, which is the Redis. So this one will be the shared cache across multiple application instances, and then you will have a persistent storage, that's it, means your database. Okay, so guiding principle will be here for principal software engineer. He will be discuss about multi-level caching here, like local cache and then Redis distributed cache, and then high availability cache warming. Cache warming means let's say you will at application restart, okay, the cache will be empty, so that time just store that value in a hard disk, and then at application restart time read that value from there, so that initial cache miss will not happen. Okay, so cache warming is that. or let's say I know that the traffic is increasing after some time. Okay, so I will already load that data into cache, okay, so that there will not be a bombardment of request on database, okay, during the cache miss. So that is the cache warming. Okay, you are warming up cache earlier, and then metrics, cost optimization, and fault tolerance. So now follow-up question 1. So let's discuss about 10 follow-up questions here, okay, for all the level, senior, for software engineer, senior software engineer, and architect. So follow-up question 1 is why you have used here HashMap and doubly linked list. Okay, so software engineer will say that HashMap provides order one key lookup, right, and while doubly linked list maintain the access order together, they allow get and put to execute in the constant time, order one. Senior software engineer will say that a single linked list would require order and removal, right? For single linked list, you don't handle that previous pointer. So if you need to delete it, you need to traverse the entire list. You cannot go previous element, okay? So because we don't have a reference to the previous node, the doubly linked list is allowed to move and removing nodes in order one complexity. Now, principal architect will answer for this is this combination minimizes latency while keeping implementation simple. It's the standard design for an in-memory LRU cache. Follow-up question 2 is, can you make it thread safe? So for thread safe, see, software engineer will say the simplest approach to is synchronizing get and put method. Okay, just use synchronize keyword for get and put method. That will be the simplest one, although it reduces concurrency. Okay, so senior software engineer, he will say that better approach is ReentrantLock and ReadWriteLock. I told you that we will discuss this thing here, or concurrent hash map with explicit locking for the list. See, here we are using HashMap and doubly linked list, right? So for HashMap, so if you use concurrent HashMap, it will take care, okay, that your thread safety. But for linked list, okay, explicitly we need to add lock there. Okay, so this is how, that is the one way, and the other way is ReentrantLock, ReadWriteLock, and then we have seen synchronized map, synchronized block also. Synchronized keyword also. Okay, so avoid one global synchronized lock. Why? Because it limits throughput. So ReentrantLock and ReadWriteLock, if we talk about here, see, ReentrantLock, what is that? A ReentrantLock allows only one thread to enter the critical section at a time. Okay, let's say you have a one block of code, okay, which is modifying your doubly linked list. So one thread will enter at once on the right. So that is the critical section of the code for you. So let's say thread A is working on that. So thread A has acquired the lock, okay, for that critical section. Now thread B and C has to wait, okay, even if B and C only want to read that data, but still they have to wait. For example, we created something like this. You have one ReentrantLock class, okay, you create an object of ReentrantLock class, and then in this get method, just call its lock method and finally unlock. We just saw it, right? And then same, so it is very simple, easy to implement and safe. But what is the con here? No parallel thread, no parallel reads and lower throughput. Okay, other threads have to wait here. Now second is ReadWriteLock. So now you will have two locks here, ReadLock and WriteLock. Okay, so see, ReadWriteLock has two locks, read and write. Multiple readers are allowed simultaneously. So now reader A, reader B, reader C, they all can read simultaneously, all can execute together. But if a writer arrives, okay, in that case everyone else has to wait, okay, until writer is writing, doing the modification. So the syntax is like this: ReadWriteLock class object, you will be creating something like this, okay, using reentrant ReadWriteLock method. Okay, this is the class and this is the interface, and then it will have this ReadLock and WriteLock class, you will call it, method you will call it, and then so the normal cache, for normal cache, get is something like this, would usually use ReadLock, and put would use WriteLock. Okay, now okay, why ReadWriteLock is not useful for LRU? Because get is also modifying your data, right? So you don't need read lock there, okay, you need write lock also, that's why. So people often think ReadWriteLock is better, but actually not for LRU cache. Why? Because get doesn't just read, it also moves the node to the front, right? Let's say you have a list like 5, 2 and 7, and suppose we call get 2. Okay, so now what you will do, this 2, now it will become something like this 2, 5, 7, right? Because it will move to head and towards head, and then get is actually write operation here, right? So therefore get also needs write lock, which means there are almost no read on the operation here, and so read write lock gives very little benefit. This is why this is the excellent interview point. Okay, so they will ask you and you should answer, you should be able to answer this. Now concurrent hash map and explicit locking list. Okay, this is what I told you, that you can use concurrent hash map, right? So okay, let me, okay, I have just updated the format, fine. So now concurrent hash map. So for hash map though you use concurrent hash map, and for list you just use the explicit locking. Okay, this is much better design. Instead of protecting, okay, instead of protecting everything, okay, protect only the linked list, that's it. The map itself doesn't need locking, and only list operation do. So for example, you will create a map, okay, something like this, of integer and node type, concurrent hash map, and then you will create one lock also, okay, ReentrantLock, and then let's say you are doing here lookup operation for on the map, right, get map. So no lock is required here, but if you are moving the node, in that case you will log that list first, and then you run your remove and insert function, and then in finally unlock that list. So this is how you will do it. Okay, only the linked list is protected. Okay, so same for eviction also, right? So for eviction you will call this lock, and then in try block just remove that element and remove that element from map also, and then in finally block unlock it. So the expensive hash lookup happens concurrently, only the list update is serialized. This improves the throughput. Now what is global synchronized lock? That is the next question. Okay, so global synchronized means you will use this synchronized keyword on get method, let's say, okay, or on put method. Or one more thing, you can create a synchronized block. Let's say you have a one lock object, and then you will synchronize inside a synchronized block, you will use this lock object. So everything is protected by one lock. Suppose you have a 10 thread, okay, they are calling get method, and one thread will run, okay, and then other will wait. So everything will wait, even if they are access different keys. Okay, they are not accessing the similar one, but the different keys, but still they have to wait. So this becomes the bottleneck. That's why you use that. Okay, what happens? So follow-up question 3 is what happens if capacity is 0? Capacity is 0 means you cannot insert node into the cache, right? So no entries should be stored. Okay, put method return immediately, and get always return the cache miss. Senior software engineer will say that check whether the value passed to the constructor are valid before creating the object, right? If the value, let's say capacity is -5, so -5 is not valid, right? So you will not create an object. So you will check the value first, validate the value first. Now principal or architect will say that treat 0 capacity as a valid configuration and avoid unnecessary allocations. Okay, follow-up question 4 is how would you add expiration or TTL there? Okay, so in TTL, very simple, software engineer will say where you just add the expiration timestamp. Okay, so you have created node, okay, of key and value. So with key and value, add one expiration time also for that particular node. Okay, senior software engineer will say that remove expired entries during get method and background cleanup thread. So whenever you are getting that node, that time only do the cleanup operation. Principal architect will say that you should support absolute TTL, sliding TTL, lazy eviction, and scheduled cleanup. Now what all these things are? Let's say absolute TTL means the cache entry expires after a fixed time from creation, regardless of how often it is accessed. Okay, so I'm saying that after 5 minutes this node should get deleted, even if you someone has used it 5 lakh times also. Okay, and then sliding TTL is the expiration time reset every time the entry is accessed. So frequently used items stay in the cache longer. Okay, so it will slide. This is the sliding TTL, means okay, you have used it now, let's wait for some more time. Okay, so something like that. Now lazy eviction, it means that expired entries are removed only when they are accessed. Okay, and avoiding continuous background cleanup, because background cleanup will make your system slower, right? So that's why. And then schedule cleanup, so background task periodically scan the cache and remove expired entries even if they are never accessed. Okay, so now follow-up question 5 is, can you support persistence? Can you support persistence? So persistence means cache persistence, whatever data you have in cache, do you need to store that? So we have already discussed that yes, during the startup time, store the some entries of the cache, okay, in the disk, and when you start your application, so just read it from there. So what software engineer will say, we can support persistent by periodical serializing, okay, or saving the cache content to the disk or restoring them when the application restart. Okay, so this prevent the cache from starting empty from every restart and reducing cache misses and improving application performance during a startup. Now senior software engineer will say that okay, to support persistence, okay, to support persistence, I would periodically take a snapshot of the cache and save them to the disk. So snapshot he will be taking. If the application restart, it can recover cache from the latest snapshot, okay, instead of rebuilding it from scratch, reducing startup time and avoiding unnecessary cache misses. Now principal architect will say about this is, at principal or architect level, I would avoid persistence in memory LRU cache and instead use a layered caching architecture. So he will be using layered caching architecture there, application, then Redis, and then database. Okay, so Redis provides a shared durable cache across application instances. So the local LRU acts only as the fast in-memory cache. Whether to persist the local cache depends on business requirement, as Redis and database can rebuild the cache after the restart. Okay, so you are storing that in a distributed cache, which is called Redis, instead the external disk. Now follow-up question 6 is related to how would you distribute this cache. So software engineer will say, I will use Redis. Senior software engineer will use consistent hashing. I have created a video on this, okay, system design video, so you can go and check that playlist. Then cache replication and multiple cache nodes. Okay, so you need the reliability, so you just replicate the cache nodes, and then you should have the multiple cache nodes for the availability. Okay, in a cache cluster, let's say. Principal architect will say that to distribute the cache, I would use multi-level caching architecture. Each application instance has its own local cache, local LRU cache, okay, for the fastest access, followed by the shared Redis cluster. And finally, the database. Redis uses sharding to split data across multiple servers for scalability, replication to keep the backup copies for high availability, okay, and failover to automatically switch to replica if a server fails. The local LRU acts as a near cache. Okay, so local LRU will be acts as a near cache, which will fetch the data quickly. Okay, now reducing network calls and Redis and improve the response time. So he will get it from a local server only, and you don't need to make different network calls. Okay, and then response will also come faster here. Follow-up question 7 is related to why not use linked list map here. Okay, so here we have used Doubly linked list and HashMap, but not LinkedHashMap. Okay, so why? So software engineer will say that LinkedHashMap already maintains the insertion access order and can implement LRU cache with less code. So you can use that, right? So for example, new LinkedHashMap, and then capacity and 0.75, that's a factor, and then true. Okay, senior software engineer will say that in interview, implementing the data structure demonstrates understanding. In production, LinkedHashMap is acceptable for single threaded use cases. So in production, though, we will use that. But in interview, you need to tell the understanding of the code, right? So that's why we have used their HashMap and doubly linked list. Principal architect will say that for advanced feature like TTL, matrix, custom eviction, and concurrency, a custom implementation provides greater flexibility. Okay, so that's why custom implementation. For custom implementation, use the basic data structure and then modify it according to your need, right? Okay, Now follow-up question 8 is related to how would you test this implementation. Okay, so software engineer will say that he will test get method, put method, and then update existing key, eviction policy, capacity 1, capacity 0. Senior software engineer will also test its concurrent access, TTL, large data, and stress testing he will do. Principal engineer, he will do the production testing with load testing. Okay, second is chaos testing. Now what is chaos testing? Chaos testing is like chaos engineering. Okay, so is the practice intentionally introduce failure into a system to verify that it can handle them gracefully without impacting users. So you are intentionally adding the failure and checking whether it is how it is reacting. Okay, your system. Then memory leak detection, performance benchmarking, and then failure recovery. Follow-up question 9 is related to what if values are very large. If values are very large, don't store that in a cache. Okay, store only the reference and store in a some S3 bucket or somewhere the main content. So software engineer will say store references instead of copying large objects. Okay, senior software engineer will say compress large values or split them into external storage. And principal architect will say cache store metadata while large object remains in object storage. Okay, so cache will store its metadata, and then in S3 bucket or somewhere store the object. Follow-up question 10, this is the last one. So how would you monitor cache performance? So software engineer will see, he will monitor cache hit and cache miss count, and then according to that he will measure the performance. Senior software engineer will add its cache ratio, eviction count, memory usage, and then expired entries and average latency. Okay, and then principal architect will say that he will monitor few things like performance, okay, then reliability, capacity, and business. So now what will come under that? So in performance he will check heat ratio, then P50, P95, P99 latency. Now what is P50, 95, 99? P50 latency means 50th percentile. Okay, 50% of request completes within this time. Some time will be given and you need to follow that. Same for P95. Okay, 95% of the request complete within this time, and same for 99. And request per second also he will check how many requests system is getting per second. Reliability, so node failure, application lag, and error rate will come. And for capacity, so memory utilization, eviction rate, and object size distributions also. Okay, and business, so he will check database offload percentage measures, how many database requests were avoided because of the cache served them instead. Okay, so you have not hit the database, cache served those requests, and so you will check that. Okay, database offload percentage, and then cost saving, and then response time improvement. So that's it. Thank you.